Yeah. Are you guys able to? Are you guys able to log in web work?
Yeah.
Start working now. Any question about what we were doing yesterday? Kylie, have you heard any question?
First, I had a couple questions about like I don't remember the problem, but another question that was when the next homework will be due, and like when we will be getting our next set of homework.
We are going to talk about the next session. Normally we get 1 week. The first assignment was due the 20th. I think it's whenever a new assignment is being assigned, the date is specifically on that, like the title of the assignment. So when it's being assigned, like if I assign today, it might be due like the 22nd. Normally that's like around 1 week. Okay. Everyone was friendly to Kylie. We're doing this weekly leader thing for the first time. I hope you can get used to it, and then it's nice to have someone that's one of you all, right? I think she's doing a wonderful job, right? She's really supportive and friendly. Yes. Thank you. All right. So today, if there's no question, I'll start the next section. We went over most of the questions for the first assignment. All the questions that I was doing yesterday, in hope that it will bring back the memory that we had from F1. Any one of those questions seems to be harder or you don't remember questions. Okay, we can still review some specific method or specific type of integration when we see it. So we won't be able to cover everything in a really short amount of time. So when we see new question, we'll start try to relearn them or find ways. Oh, I think from the actual. I'm just gonna. They're all in the same, they're all in Jersey. I'm just bringing up to the front today. They're all in the content section. They're supposed to be in the PowerPoint folder. I'm trying to grab it out of there. In today's section 5.5. It's not there. Chapter 5 is really Calc 1 material. I used to just start right away with chapter 6, but then I realized that many times still have to. I still have to review chapter 5, even if I try to start with chapter 6. So start with chapter 5. Okay. So it's one of the methods you might have already learned, and like I said, it's a review. But if you haven't been studying integration for a while, it might sound new. How many of you still remember substitution method? Okay, cool. So we're gonna try to work out an example. Like this one. All the solution already there. But let's look at a bigger question instead, so you kind of see why substitution method is necessary. Right, so this is one of the questions we will have to use substitution to solve. Let me see how many of you are able to figure out the answer. Just want to say for sure, remember substitution method. It's kind of like the name substitution. You make something as a substitute for something else. That process of assigning a new variable allows you to simplify the integration. We started talking about it yesterday. When we're solving a question, most of the time, we're not immediately giving out the solution because solutions often are not clear. So what you have to do is look at this question and change it to something similar, change it to something familiar, so you can see through how it here at first to see how it's supposed to be in the end. So changing the format of the question to the one that actually has a solution. That's all. If something does not have a solution, maybe we look at it again from different perspective, using different variable, then we will have a solution. Okay. So if you slightly remember substitution method, what do you substitute? How do you do the substitution? Substitution method sometimes is being called user, right?
Yeah, you take like a portion that will derive to another portion of the function,
Yes.
and you'll like write it with u, and then you'll find du.
Right. So, like this question, what do you think should be the u and du?
16 plus 3r squared should be 6r should be.
Right. So we would make part of the question the u, and part of that will be the du. And the process of changing the question, converting the question, is key steps in substitution method question. So like you said, we would make u equal to 16 plus 3r squared. We have very good reason to do so, because the main difficulty in this integration is, this big thing in the denominator. If the denominator was just u or root of u, then it will be a lot less complicated. So we are really transforming the bottom part of that into that whole thing. But this is what happens when you give some, you take some. So if you are making this part simplified, less complicated, you might very likely making the other part more complicated. So we're gonna figure out if we are doing this, we converted this into this. This becomes root of u because we're doing substitution. And then so what happened to the top part of it? That part we have to reason with it. this is called a differential. So if you have the original equation have a differential of the original variable, now you are making up a new variable. So you have to find the differential of this new variable, compare with that. So we need to find the connection between the two differentials. Now this u, the process of finding differential is similar to the process of finding the derivative. So we will find the u by first find the derivative. Derivative of the u is 6r. Yes, thank you. So we will have 6r. But then if you have a differential, you have a d on this side, you have to have a d on this side, the other side, because the differential equal to another differential. You can't be like, that's not it. You have to multiply it by the differential of the independent variable on the right, which is r. So this is the official definition that we had in Calc 1, which says the differential of a variable is derivative of the function as a variable multiplied by the differential of the variable. So dy equal to y prime times dx. That was originally the definition, and we're just changing it to new variables, new letters. But the fundamental idea is you gotta have a derivative, you gotta multiply the differential, because this is supposed to be equal another differential. It's like a balance. You got a differential here, you gotta have a differential there. Yeah, forget the differential. Very often I see my students in Calc 3, they make mistakes because they tend to forget the differential, forget to write the differential part of it, and then you will see some problem in the long run. But at first it's just a habit. Are you keeping the format or are you forgetting part of the format? So there, we realized that 6RDR, which was in the numerator, now become du. Okay, so this is a substitution process. We did a substitution with a new variable, and then that affected the rest of the part in the integration. That become this. Notice that I did not write the integration limit. It's a computation question. Eventually, you have to handle the limit, but we can do it in steps. You finish your indefinite integral, and then you put in the number and finish the definite integral. But let's first finish the indefinite integral. So we're gonna have to integrate this. According to what we were talking about yesterday, how do we finish the integration? We're supposed to calculate this.
Rewriting this u to the negative 1/2.
U to the negative 1/2. Thank you. So we change it into a power form. So yeah, it tends to work. So integration u to the negative 1/2 power. Again, this is not calculation. This is converting to a different format. So we can now follow the power rule for integration. Now this step, now find power rule. The power rule is the integration method. Now with the power rule, we can lose the integration notation, which is that part. We gotta remember, when do we keep that longer version of letter S, like continuity, summation, continuous version of a summation. You have that, you have that. Then once you finish integration, you don't have that anymore. So we would have to remember, when do we keep it, when do we remove it. So it's going to be u to 1/2 plus 1 is positive 1/2 power, the power plus 1. Negative 1/2 plus 1 is positive 1/2. And then plus c, still doing indefinite. And remember the u is this. And the original variable is r, so which means this is r equal to 1, and this is r equal to 0. So I cannot put in u equal to 0 or u equal to 1, because u does not equal to 0 and u does not equal to 1. Because the r is indicating that our variable is r, therefore that 0 is r value, that 1 is also r value. So if you want to finish the calculation, you have to convert it back to the variable r. So this is equal to, let me try to rewrite. This is divided by 1/2. This is actually 2 as 1/2 power is actually root u, which means this is actually 2 roots of, this is u, roots of 16 plus 3r squared. So we're writing it back to, this is something additional to a substitution method. In a substitution method, you are using a new letter. You're entering a new variable, and that variable is not part of the original question. This new variable is something you invented. You artificially put it there to help your calculation. Some people don't like the u. You can use a, and you can use p, whatever letter. But then it's not part of the answer. So eventually you will have to go. U is equal to 16 plus 3r squared. So eventually you have to write it back to the original variable, and that's something that we have to remember, the substitution method. Now we're done with the indefinite integrals. Final answer will be this. Now to do the calculation of the definite integral, we now know the formula. We'll calculate 2 roots of 16 plus 3r squared. And we're going to calculate the value of this at 1. We're also going to calculate the value at 0. We subtract the two numbers. Any question? I hope you can do the rest. Question? This is one example, and then that really hope it bring back some of the memory when we were trying to figure out how to do the substitution method before. And I'm gonna try to go through the PowerPoint. Hopefully, we teach the session. But in the meantime, this is a very typical example of substitution method. Any one of you already have the answer? You still have your card. If you don't have the card, I hope you still have the image of the card. Bring this up, right?
Oh, hold on, wait, okay, I think I'm gonna screw something up here, hold on.
Once you finish enter the answer, have your card face down, because especially if you sit in the front. If the scanner is scanning, no matter whether you're holding it or not. You pick up image and change your answer. All right, anyone else?
Oh, that's why
Okay, so this is,
okay, I think I figured it out. Hold on. Just further and,
that's right.
yeah, made a miscalculation on mine.
You can always let me know afterwards. I mean, one of the purposes of this is to make sure that we catch the attendance. James? You could see, yes, but it's supposed to be. Okay, yeah, like I said, if you are at the front and your card is facing up, it might accidentally scan the wrong information. So if you're not trying to enter answers, then you should make sure the image is not visible to the scanner. It should be A. Let me finish the rest. If we put in the number 1, then we would have 2 times 16 plus 3, which is 19. That's when when you bring the number 1. When the r equal to 0, it's 2 times 16. So that is really 4. 2 times 4 is 8. So 2 times root of 19 minus 8 is the answer. For calculating the definite integral, we find the evaluation at the upper limit and then minus the evaluation at the lower limit. Let's review the idea of substitution method. And the root of substitution method is coming from chain rule. Whenever you are trying to analyze this function, if we find the derivative outside of power 10, inside becomes polynomial. So according to the power rule, we will bring the power to the front and the power minus 1 as power rule for differentiation. But we have a big polynomial inside. We have to differentiate the inside. The derivative inside is 2x plus 3. So this big power function, power 9, multiplied by the derivative inside, that's the calculation according to chain rule. And you can see it can look a little bit long, and we don't dare to calculate the power of 9, because if you say the x to the 9 to the power 2 times raised to the power 9 is power 18. So this is a power 18 degree 18 polynomial, which extended to a really, really long polynomial. So it's better to keep it in that format, in the power form, rather than expanded. Okay, so this upper half, this 2 rule, explain the process finding the derivative in reverse. Integration of this derivative would equal to the original. So this function had this antiderivative. We would not know if we haven't calculated those chain rule process and realized integration of this gives you this. This is one example showing that sometimes when the integration is integrating a multiplication, when the special thing we observe that situation is one of these functions looks like it would, how do I say? It looks like it would fit a derivative format. So it looks like if you got, well, if we have a 10 to the power 9, it looks like a power. So if we see or vaguely see a format of different derivative inside of that, that may be a possible candidate for substitution method if we see a derivative function. So that one. So this is going from differentiation perspective. If we don't have that, and then we can go by substitution method. So in that case, we will look at that function. The first idea will be, hey, I have to integrate a function that has a power of 9. So when we are trying to find integration of a big power function, there are 2 things we can do. Number 1, you can calculate it directly, which is expanding the entire polynomial and using power rule to integrate them term by term. If we do that, the power 2 raised to the power 9 give you power 18. This will be a power 18. A algebraic computer can do it. Power degree 18. It's a really long polynomial, but we can integrate it one by one from degree 18, degree 17, degree 16, down to a number. So that's going to be more time consuming if we do it manually. That's the first method. We will call that direct integration. The second way is, instead of expanding the power 9 to a degree 18 polynomial, we do not expand it. Instead, we condense it. So one of the things you can do, this is a power 9. If we do not think that is 3 different terms, if we think of it as one single variable, then this will be a power 9. If that was a variable u, this will be u to the power 9. There's nothing else to it. It makes the whole thing immensely simplified, right? So, and that's another thing. So you either expand the whole thing into detailed calculation, or you transform it into something completely different but identical in nature. All right, so we go by it that way, and that's what brings out integration. One of the main reasons substitution will work is substitution allows you to change your integration to a new one, in the hope that this new integration will be easier to calculate. So sometimes I would substitute a variable, and I will carry out the calculation because I'm not the very like those genius students that can do all the calculations in their head. I have to see it, so I have to write everything out to know whether that works out. So I would do several different ways of substitution to finally decide, hey, this way is a lot simpler, and that way it takes much longer time. So you have to try and substitute in different ways to see which one works better. With experience, we may get the idea how to do assertion substitution. The more questions we do, the better we get at assigning the new variable. But this one, the most direct thing you can see is if that were the u, we would get it really simple. So we would try to let u equal to this variable, and then this part immediately becomes u to the power 9. A substitution is one thing we have to follow is if you substitute everything. So if we substitute this part becomes u to the 9, that has to be something about u, that has to be something about u. So if you substitute variable, you make sure you substitute every single piece of that integration into a form of the new variable. So we would do it little by little, like first, if that was u, it's u to the 9, so that part gets substituted. And then if this is a u, then du would be the derivative times dx, right? So that's our du. And what do we want to find du? Because we were hoping to find a way to substitute the dx, right? So we can see that 20x plus 30 dx, now we have a 2x plus 3 dx. So from there, we realize that this is actually, you bring out the 10, you have 2x plus 3 and then dx. So the 2x plus 3 and the dx, that part is identical to du. So this whole thing becomes 10 is still there, u to the power 9, and then that's the du. So it becomes something all about u. The integration question with integration variable x now becomes integration variable u. So we're doing an integration about this new variable according to power rule. Remember, when you were integrating, and last time yesterday, with a t and x, we realized when the variable, when these two are different, we have to integrate really differently. But right now, we finally made them all the same variable. So pi power rule, we raise this power 9 to a 10. So this integrating into u to the 10 over 10. So the number 10 can cancel the numerator 10, so that there's no more denominator or factor. So just u to the power 10 is antiderivative, so that finished the integration of the u function, and then we're going to go back to the original variable, transform back to the original variable because u is to this. If the question is given about x, and you have to answer the question about x, so that's why we can't answer u to the 10 plus c as our answer, because after all, the question is all about x. That will be the final answer, and this is the entire process of using substitution method to answer the integration question. Any question? All right. It may look more lengthy than the differentiation. Like if you have that intuition, like if I find the derivative of this, I would find this. Therefore, integration this. And that's all true if we do know that initial setup. How do you know that one? Which was the answer. If you already know that, you go backward. Doing the differentiation, of course, is shorter. But since we're doing it backward, and this is a difficult part of the integration, differentiation largely follow many differentiation formula. But integration, when you look at the differentiation process, you still follow the differentiation formula. But integration have a lot of different formats, and one of the common thing is almost every smooth function has a derivative, but many continuous functions do not have an antiderivative. So integration do not always have an answer, but differentiation almost always have an answer, unless the function has sharp corner or discontinuity, and that would be a thing. Okay, so what we are observing from here is that, like right here, okay, so one of the things we can see is that this function, that's the derivative. Whenever the function and that function's derivative show up in the same multiplication, we would do substitution method. And it's something that we often ask ourselves, not right now, we're not doing anything super complicated yet, but later we're gonna see a lot of multiplication. So when you see this multiply this, you'll be like, do I use substitution method? Do I do the integration by part? So do I do the other method? So we have many integration techniques, and then we might have some problem choosing which method works better. So from the beginning, we'll try to find some characteristics, something special about that method. So later on, when you see it, you know when to use that method. So as far as substitution method, you should always see something that this function, that's the derivative. When the function and that function derivative show up in the same multiplication question, in the same integration, which this is multiply this, or integrating that multiplication, that's when you use substitution method. When these two has no connection whatsoever, that often will be indicating that we should use integration by parts. Integration by parts is the reverse version of the product rule. Remember, product rule is when we have two functions multiplied, right? We find the derivative, use the product rule. But with integration, you don't have those product rule have summation. You don't have the summation. You don't have both parts. You only have one of them. That's the same. We have to do part by part. Right. That's when the two functions have no connection. But we're doing something that do observe some connection. All right. So according to chain rule, when you have a compositional function, you often have to find the derivative of the outside function, which is this, right? And do not change the inside. Then you multiply the derivative of the inside. We don't find the derivative here, but we find the derivative here. So that caused a symmetrical look of the derivative. So that derivative looks like this is the original, that's the derivative. So the original function and the derivative function is showing up in the same thing. So when you have the integration question, right, you have this derivative and the inside is the derivative. They're in the same format, the same multiplication. We would have the antiderivative that's caused by chain rule. So following that idea, we can change to different format. And one of the ways is, since this looks a little bit cumbersome, some people find it difficult to identify the relation. So instead, we make this one equal to u. So the format looks instead of f prime g of x, and we have f prime u. So if you make the inside part, the g of x, make it equal to u, then the g prime becomes u prime dx. And then the u prime dx becomes the u. So that the look at it looks much simpler. Integration of derivative equal to the original. So logically, it's more straightforward. Those are two different formats, depending on which one is that you are more used to. I do use the U substitution more often than the original intuitive. Any questions? And there's a couple of examples. Let's see. Okay, so we're going to do integration by substitution. Here you see a multiplication there. And again, now we're looking at a situation where we will not have a formula for the integration. And that's why we're calling it an integration method, because it's a special way for integration. We know how to integrate sine. I hope you still remember. We integrate sine of x dx. What do you have? Negative cosine. Because that was the original. If you find the derivative cosine, you have negative sine. So therefore, negative cosine, we have positive sine. So there will be if you're finding the derivative of the whole function, you get a negative. Even though the negative is not here, not there. But if you're differentiating sine, integration of cosine equal to sine of x, because this is the one we're finding derivative for. Just look at this, therefore this, no more negative. Just try to review the difference between the two. All right, so now we have something slightly different. We do not have integration of sine itself, we have something extra. And also instead of sine of x, we have sine of x squared plus 5. And that would be not very convenient, right? So when something is not so easy to handle, what do we do? Simplify it. Right, so if we try to do a substitution method on this example, what do we assign as u?
X squared.
Plus 5. So what we do is we make u equal to x squared plus 5. You can try yourself on paper. You don't have to look at me. You can also try it and see if we are getting the same thing. So that really changes this part. It becomes sine u if x squared plus 5. This is actually sine u. Right, and then I changed that part, but remember a substitution, you have to substitute everything in there. So I substitute this part. And what we have to do next is make sure this one and that one is included in your process. So let's look at how do we do the substitution of the equations. What's du? 2x dx. Because derivative u is 2x, that has to be a derivative. So multiply by dx. Again, we have to have this habit. Whenever we handle the differential, make sure it's balanced. You got d, and therefore you got d on the left and right. Okay, so now that gives us the idea that now we have a way to understand if we multiply x with dx, which is this, x multiplied by dx, that's the test that we have to substitute, right? We have this part that equals sine u already. So the x times dx equal to what? How do we substitute x dx? It would be 1/2 du, right? We get rid of that 2 there. So we divide both sides by 2. And then we will have the x dx. And therefore we realize what we have here is going to be 1/2 divided and that would be this x dx equal to 1/2. Everything that we have after the integration notation, this multiply this is a multiplication relation. So when you multiply 3 different things, the order can be rearranged. So we did 1/2 at the front. Even though it's supposed to be 1/2 times u, any student write 1/2 here and then u there, that's fine too. But we do have a habit of having a number in the front or even outside the integration notation, because this makes it a lot clearer to look at. So we will do that. And this is equal to move the 1/2 to the outside, and now we have an integration of sine u du. Sine u du. Right, so that's pretty much the integration of sine function. Over here on the board, I have integration of sine function equal to negative cosine function. So the answer will be negative 1/2 cosine u. It follows our integration formula. Any questions so far? Are we done?
No, we have to.
Okay, thank you. Yes, we do have to convert it back to the original variable, negative 1/2. That was the original substitution. So we know the use is x squared plus 5. So x plus 5 will replace the u. That would be the answer. So however the question is being asked, and that's how it's going to be answered. It goes the same way with sometimes we do a numerical calculation. When a question is given by a two decimal number, right? So whatever answer you're answering, we're not answering with integer or one decimal. Instead, we answer two decimal answer. You can make it more accurate, like two decimal or four decimal. We should at least have two decimal answer if the question is given with two decimal years. And that's this is another question. When you have a number in the integration question, what would happen to that 5? What happened to the coefficients? So let's go like this. If we have integration of cosine, which is mentioned that integration of cosine of x dx, what is it equal to? Sine of x, because the derivative of sine equal to cosine of x. Now we're asking integration of cosine 5x dx. What is this equal to? I think if you have cosine x, then you have sine x. If you have cosine 5x, you have to have sine 5x, right? So what happened here? Is it 5 or 1/5? 1/5. So that will be the answer. Thank you. So we kind of see that they still follow the same pattern. This, and then we have cosine 5x, therefore we have sine 5x. But then the 5 have to be, you have to make it up for there. So so then we get that 1/5 for. So this can be explained by substitution method. So now we have those, they're kind of like a formula. Whenever you have a number there, you have the same number there, you gotta 1 over that number here. But here are the reasons. The reason is the substitution method, and we kind of see this once we do a few questions similar to it. For example, we start by letting u the 5x, then du would equal to 5. The root of 5, u equals 5. 5x is 5. And we still have to have the on the left side. This different variable. Variable x, variable u. Differential here, differential there. This is try to make the substitution for the variable and make the substitution for the differentials. Going back to how we substitute, we'll have everything replaced properly. So here it's going to be cosine u, 5x u. And here we have ex, and we have ex over here. So if you have 5 ex, it would equal to u. But if you only have ex, then it equal to 1/5 u, right? You have to get rid of that 5 in order to get the dx, right? So because of that dx, we realize dx is actually equal to 1/5 u. So after substituting that part, we substitute this one by 1/5 u. But then again, as a tradition, we bring the 1/5 to be outside of the integration. Inside the integration, we have cosine u du. According to the integration formula, the antiderivative of cosine u is sine u. Now, since u equal to 5x, then this is actually 1 over 5 sine 5x, because u equal to 5x. I have to put parentheses because there's two things in here. That one, there's only one variable, so sometimes I skip the parentheses. And I finished the solution from the original integration question. Now it's the integration question. Any questions? I think most of the textbook will carry the plus c here, but I did not write that plus c. But everywhere that has integration notation, you don't have to do the plus c, but with every antiderivative, you should. This is an example. See, like this is like a general version of what we're doing here. If you have a number multiplied to the inside of your trig function, and you will do 1/5 or 1 over whatever coefficient that is. So what if you have a number plus or minus to it, and the answer is it doesn't really affect the coefficient, but it does affect the inside of it. Here we have an example. So let's say you are integrating sine 7x minus 4. The antiderivative of sine is negative cosine. So we have negative cosine, the whole thing. Then we have 1/7 because 7 affected the derivative and this minus 4 do not affect the derivative. Therefore, on the outside basis only. Any question? All these questions can be quickly done with the substitution method. So this is one of the formula I never try to memorize because it's kind of lengthy. And it's not difficult to run through the substitution method essentially. So I normally skip the memorization and go directly to the substitution method because we have to learn to use substitution method anyway. So we prefer and simply substitute through. And sometimes get used to different variety of these kind of questions and you start saying, handle them quickly. So at first, when you see sine 7x minus 4 dx, the first thing I would say, hey, what if that would be a u, and that's easier. So we can see we let u equal 7x minus 4. And naturally, I want to know the du, which will be 7 dx. Derivative, negative 4, the minus 4 has 0 derivative. So then this box is my key term for substitution. Now this, which is that is equal to integration of sine, that is u, 7 minus 4 equal to u. And then because of the du equals 7 dx, so dx equals 1/7. So that's substitution method. And then we finish this by bringing the 1/7 to the outside integration of sine u du. Is marker too light? Are you guys still able to see? So it looks like it's writing on the board, which is more visible. And then we integration of the sine u to get negative 1/7 cosine u. This antiderivative of sine is negative cosine 1/7, which is coefficient. Right, and then what's u exactly? U is the 7x minus 4. Get better now. So we write back to the original variable, this question equal to negative 1/7 cosine u. U is 7x minus 4. And then let's see, so that's the same answer you see on the board. So this will be the whole process we should do it. It's not too hard to do it, and then the process repeat itself if you change the number. So for example, what if that was 5, that was plus 3? It would be the same thing. It would be negative 1/5 cosine 5x equals 6. So similar pattern follow. That's why we got this formula for. So eventually you realize that b will only be part of the inside function, but it doesn't affect the coefficient. Because that one will produce a number for the derivative. This one has 0 derivative. So it doesn't show up here. So some of the situations where people sometimes like, how do I do that? And sometimes simpler question is more unfamiliar. People tend to realize that this is a simple question. Somehow I don't remember how to do it. And so substitution kind of helps with that. All right, so I'm going to ask you, what do we do substitution for? Like u equal to, say u equal to, yes, u equal to negative 3x plus 1. Okay, thank you. So we would let u equal to negative 3x plus 1. And that will guarantee that what we have is an overview. The whole denominator part including u, and we still have to work on getting this part. Okay, so that's the reason now we have to study the differential. So the u is equal to -3 dx. And we're hoping to find out what happens to the dx. Okay, so now we have dx, almost have the dx. So if only we get rid of the -3. So we divide both sides by -3, it's -1/3. So we're getting out of get a representation of dx from that equation. Simply divide both sides by the -3, and that's what we have. So we substitute the u into this part and substitute dx for that part. This is a simple multiplication, so it's a tradition to bring the -1/3 to outside of the integration. So you can already had it there. So I guess it's better just write already -1/3 u. Okay, so let's try to correct what we have there. So it's -7/3. I'm collecting all the numbers, and they're all outside. Now you have integration for u. So clear, well, remove all the numbers and make the multiplication to be outside. And I remember that number you carry, and you don't have to do more calculations to it. And this is the part we actually have to finish integration of. So how do we integrate 1/u?
So we leave out the log of the absolute value.
Yes, thank you. So it will look like this. You still have the -7/3, but there's no worry, just finish writing it. And then this part is the actual integration, and that is giving us absolute value of u. Right. If you are integrating the u functions, you're already done. But we're not integrating the u function. We're integrating this. So we still have to write it back to the original variable, and the original variable is x. So the answer is going to be -7/3 ln of -3x plus 1. That's about it. So this will be the final answer. You can also try to find the derivative one more time. Derivative of ln is 1/, this whole thing, and multiplied by -3. And then multiplication of -3, this -3. Cancel this -3 with the chain rule. We'll have 7 left. So that will be the derivative. We can think backward. Like if I get this function and does this function have that derivative, and then your knowledge of the derivative helps you determine that if you did like correct calculation. This. Any questions so far? Are we okay? Yes.
On the test, if it's like a really simple problem like one you did on the board, and if we can memorize the formula, would you prefer us to still show the steps, or if we wrote it down because we memorized the formula, would that be acceptable?
It depends on whether the answer that you memorize is correct. So if you write a correct answer down, I don't care how to get it, from your memorization, from your formula card, from your own calculation, as long as the answer is correct. So if the answer is wrong, then having steps kind of explain your idea, and then I will look at your calculation. I probably will give you some credit for presentation. Whenever I see somebody writing really nice presentation of their work, I kind of value their time and effort in there, so I do give them some credit, even though the answer is not exactly on the right path. So it depends on how confident you are with your answer. You know for sure I have everything correct, and there's I don't see the reason you have to put a complicated solution to it, even if you already have the right answer. But if you're not sure, then it will be it will waste the time to explain why do you think this is the right answer. So more the reason to write things down if you're like halfway there. Any other questions? Right, I'll let you do some work. I think I have a few more example in this set. Try this one. Okay, so this is similar to the one we just did. We're trying to find the antiderivative of x cosine 2x squared. See if you can get the answer quickly. No. You can always send your answer to the multiple calculations. You got a different answer on the second process, then it's okay to raise your hand. The corner is not, okay, I got it now. The picture is bright, making it hard to see. William, that's not the right one. Can you walk over so it won't be so shiny? That's not the right one. See if you answer that's not right, though. Logan, have you tried it again? Yeah, let me go through the process again, and then we see where's our differences. And so what do we do for the u substitution? U equal to squared. And u is equal to 4x dx. Because derivative of 2x squared is 4x, but derivative is not enough. You have to multiply by the differential. And then we're looking at how do we do substitution. The 2x squared is substituted by u. And then we have x left. We have dx left. So you have to think what's already being replaced to what's not. So this part, substitute with cosine u. So then you have this part and that part, which essentially is x dx. Okay. So the x dx would equal to 1/4 u. Because you have to remove that 4 from the right side. So that means the x dx is 1/4 du. So you have the u here, have 1/4 on the outside. Right, so that finished the substitution. Substitution method allows you to rewrite the question, but you then still have to solve the integration question. We're basically converting from a harder integration question to a slightly different integration question that we can solve with our integration formula. Okay, thank you. I still have Jacob and Isabel. Jake? All right, so I guess everybody already knew the answer now. The final answer will be 1/4 sine u, but we have u equal to 2x squared. So that will be the answer. If you think of it, we try to find the derivative here, and this is actually is a derivative, and that confirms our perception of what's supposed to be the right answer. So you can see the answer is supposed to be this one. All the other one has some slight problem, like this one. Why would we have a u there? But this one forget to take care of that coefficient. That in the process of doing this, you forget how the 1/4 divided. So that's missing the 1/4. This one, I don't know what happened there. You can't have the same thing multiplied. There has to be the derivative. So most of the other answer does not make sense. The final answer is supposed to be here. Okay. Let me see if we have a different question. Show me. I want to go back to Weber to show you an example in our homework that we are supposed to solve. Let me go back here. Sorry. Oh yeah, I'm supposed to assign it, like you said, what was the next assignment? We were supposed to assign 5.5. Make it December. So that's a sign. Let me try to go back and see how it looks like your sign. So then, asking these questions out. Sort of. Because I really made the password unsafe. This account is really a practice account. It has student as password and username. That's why you keep saying it's not a good idea if you do that. All right. So this is how it looks like when you are looking at our question. Basically, we're reviewing the substitution method. So you might have to. I should apologize having my question there again. Yeah, not any questions. This one. So most of the questions are not that time consuming since we kind of know a little bit something about substitution. And I promise once we started chapter 6, the number of questions perception should lower. All right, we can always do it together. Like the first question is exponential function. I realized that we didn't do exponential function with our PowerPoint example. So, but you should remember how do we integrate exponential function. We have a formula saying that integration of x is equal to, do you remember? X, yes. So exponential function is the only function where the derivative equal to the antiderivative. The original is all the same. We are differentiating e to the x, it never change unless there's something there. And we do have a little something in there. So now we're integrating e to the 9x minus 2 dx. So what we do is we do a U sub. You make u equal to 9x minus 2, then EU. So you got this habit, whenever you're doing U sub, you immediately write out EU, because we're gonna need it anyway. Derivative is 9 multiplied by differential. So that's really the transformation, the substitution tool. So with that, we realize this piece is to the u. With that equal to u. And this part have a dx that we need to replace. This is a dx. Get rid of the 9. The 9 goes to here. So that's 1 over 9. See, I can split things with this on the board. Continue. So that's substitution. So essentially, this is using all values of substitutions to finish the integration. Now we're back to our original form. You're integrating e to something, you get the same thing. You have 1 over 9. So that finished the integration, which we apply the same formula to begin with. So we would go by something that we cannot apply formula, use substitution. Now we have something we are able to apply formula. Right back to the original variable, we have 1 over u e to the 9x minus 2 plus c. That's the final answer. So we go back here, and you probably have something very similar on your site. 9 e to, I'm going to use for instance 9a. This is the first question. Any questions so far? Try a few until we get the user. Second question. Something special about substitution method, we talked about it at the beginning. The reason substitution would work is because we add a function, we also have derivative of the function. For example, this question, the denominator normally is what we substitute, because when you have a division, what's causing your problem? Not the numerator, it's the denominator. You got a big denominator, you're gonna move it away, change it to something simpler. But if you have a simpler denominator, normally there's no problem. Just finish the division one by one. But when you have a big denominator, and then realize that derivative of the denominator is 2x minus 7, and we do have 2x minus 7. So that means this is part of the u, and this is related. To put those in actual representation, we write this. You would say the denominator will be the original. All right, and therefore we have a derivative that will be 2x minus 7, but derivative is not enough to multiply it by partial. And then we're going to look at the original integration question. This is not integration. This is substitution notation. This is like a symbology that allows you to rewrite your integration. The integration was 2x minus 7 over x squared minus 7x minus 18x. So this is equal to, this is u, according to our substitution. So the number is u. Now, if you have 2x minus 7 times the x, that's all the u. So we got 2x minus 7, which is a big numerator, times the x. That two together is du. So turns out every single column is 1 over u times u. That together is the u part. So we realize that simply is a logarithm question. So this is ln of u. Again, back to the original variable, we rewrite it, replace the letter u with the letter x on. So this is actually the answer to this question. If you say if that was some of us, like we did that last semester. For some of them, like that looks new, that looks new. So it really depends on our own past experience with it. So I hope that you are following our example, because if you identify the similarity between your question and my example, it takes a lot less time. But if you do it all by yourself, a lot of time, it does take time to figure things out. Go to the math lab. We do have a couple people there that's really experienced. Any questions? Do you know what's the answer for this one? What do we do for substitution? U equal to natural log of x. Thank you. Yes. We think of the u and u. U is the original. U is supposed to be the derivative. Like that's the meaning, right? U is the original. U is the derivative of u. So you're supposed to have that derivative in there. So logarithm x, derivative of logarithm x is 1 over x. So 1 over x is a derivative part. So logarithm x has to be the original part. So the original part is what we will assign as u. The derivative part was supposed to be go with it. So it's supposed to be the u part, the x part. So we will make u equal to ln of x. And therefore du would be the derivative of ln, which is 1 over x together with the dx. So really clear about the symbology. Sometimes it's all about representation. If you follow the format, they all fit together. If you ignore the format, sometimes a tiny mistake causes like negative become positive. 1 over x becomes x over 1. So sometimes make sure the format is correct. So now we have this -5. It was supposed to be outside. It's a multiplication. So bring the -5 to the outside of the integration. Now we have ln of x over x dx. If I were to write it into a more clear format, that's logarithm x times 1 over x dx. And we made it really clear that is u, right? -5, that's u right here. 1 over x dx is a derivative of ln of x. Therefore, it's the du. Du equals 1 over x multiplied by dx. Because for calculation of differential of dependent variable, you take the derivative multiplied by the differential of the independent variable. This is a part of section 4.4. You're like, how do I do all those differential? When did we define such a thing that's called a differential? Look at the definition, but essentially it's derivative time differential. This is new differential, it's our du. So a lot of things you see, I'm trying to say this equal to this because that's how the differential has been defined. It's really symbolic. All right, so now we have this. You okay so far? That's changing the format from this, which we kind of vague about what to do with it. Now we have this. There's no more logarithm, there's no more division. And then all we have to do is integrate this. We know how to integrate u du. Power 1, right? We would apply power rule. So you finish the integration is -5 u squared over 2. Let's put it to the power rule. Let's see. Okay. Power 1. So n equal to 1. N plus 1. N plus 1. Are we okay? All right, so finish that. We have -5 over 2 as coefficient. We were supposed to have u squared, but what's u? U is ln of x. So ln of x, that's not too messy. But that will be the answer. We then look back to see how they works out. If you try to find the derivative of this, according to the power rule, you bring the power to the front, which cancels 2. The power -1, that gives you ln of x. And then according to chain rule, you have to multiply by the derivative. Derivative of ln of x is 1 over x, and that's why we have that 1 extra 1 over x. So this is the derivative, and that was the antiderivative. So the answer to the question is -5 over 2 ln of x to the power 2. That's, yes. Any question? We only went up to question number 3, but try the rest. I'm not sure where we are as far as substitution method. So I went ahead and review it again. I didn't finish. Yeah?
I was just hearing the shuffling and
Oh yeah, there's 2 minutes left, you guys. Any question? Are we doing okay? Are you totally confused? We need more time, or we're okay so far? Okay, cool. So let me know if you got any questions. We do have 22 on that section. It's a little too much. So if you see anything that was an extra part, let me know. We can do it together. Right? If you don't feel anything is hard, then we just go by it. And then you're gonna start section 1 very likely. So we talk about. I think we're talking about integration by part. No, it was the first section. But we're going by section 6.1 tomorrow. If there's a little question, if there's questions, anytime we can spend more time and try more examples. So you can always ask to slow down and work on more questions if you have any issue with the homework or anything. You have control of the pace. I didn't try to go fast. But that's it. The schedule is posted. It's on Georgia View. If you wonder when it would take test 1, test 2, test 3, it's there. Hopefully that we have more anticipation of it. I'll see you tomorrow. Thank you. Yes. Yeah. Right. We're doing those low versions of 5, and then we do the structure 6.
I did the same way I did all the other.
Okay.
So I have my work right here.
I was supposed to, I think it's the accuracy, y 5. So 5 over 14 is 1, somehow it's 2. Easier calculation, putting the time 4. I think it's the decimal point. If you use a calculator to give it like a 5 then it would be right.
5 decimal? Okay.
The computer is very strict about accuracy. Or you can use the root of 2 over 2 as your sign.
Okay.
Then it won't have issue. I often use roots for the decimal.
Okay, thank you.
Yes.
Do you understand the PI method?
Yes. Yeah. So calculation. Yes, right. You mean the tabular method for integration? With the integration by part? Yes. Whichever method that seems to work out.
You show your work.
Yes, as long as you show your work and as long as you understand the process. I can do it either way. I also sometimes use the tabular method. Whenever things are longer, the tabular method looks better.